Hello everyone! In this video, I will present how to solve the vector addition problem using OpenMP, compare the sequential and parallel approaches, and explaining why parallelization improves performance. So, the problem consists of adding two vectors, A and B, to produce a third vector, C. So each position of the result vector is computed by summing the corresponding elements following the rule C of I equals A of I plus B of I. For example, if A is 1, 2, 3 and B is 4, 5, 6, C, the resulting vector C, will be 1 plus 4, 5, 2 plus 5, 7, 3 plus 6, 9. And that's it. It is a simple problem, but you can apply the parallel approach. Let's see the sequential version now. In the sequential version, the program uses a single thread to process the entire vector. As we can see in the code, a simple loop goes through all positions of the vectors, from index 0 to n-1. And at each iteration, it performs the sum of the corresponding elements from vectors A and B, storing the result in the vector C. This approach is straightforward and easy to implement. However, each processes one element at a time, which means it does not take advantage of multiple cores. Because of that, it can become inefficient when dealing with large vectors. That is where the parallel approach comes to hand. Now, in the parallel approach, we use OpenMP to improve performance by executing multiple operations at the same time. So instead of processing the vector sequentially, the work is divided among multiple threads, and each thread is responsible for computing a portion of the vector independently. This allows the program to take advantage of multi-core processors. Now, looking at the code, the key part is the directive Programma OMP parallel for. In a complete implementation, we first include the OpenMP library using omp.h. Then we define our vectors A, B, and C, just like in the sequential version. The main difference happens in the loop by adding the directive Programma OMP parallel for, as you can see here, right before the loop. So, doing this, we instruct the compiler to automatically create multiple threads and distribute the iterations of the loop among them. Each thread executes a subset of the loop iterations. For example, one thread may compute the first half of the vector, while another computes the second half. Since each iteration writes to a different position of vector C, there is no interference between threads and no need for synchronization mechanisms like critical sections. So after the parallel region finishes, the program continues normally and prints the result vector like in the sequential version. This makes the parallel version very similar to the sequential one, but more efficient for large inputs. So why this works well? This problem is ideal for parallelization because each operation is independent. There is no need for communication or synchronization between threads. Additionally, there are no shared data conflicts, since each thread writes to a different position in the result vector. So one of the main strengths of this approach is its simplicity. The code is easy to understand and require minimal changes to become parallel. And it also provides good performance improvements when working with large vectors and scales well with the number of threads. Now, some improvements can be made, such as adjusting the number of threads to better match the hardware, because, for example, the number of threads of my hardware can be different from your hardware, from your computer, so adjusting it can get better results. So it is also possible to improve load balancing or combine this approach with vectorization techniques. And additionally, performance benchmarking can help identify the best configuration. In conclusion, parallelism can significantly improve performance for problems like vector addition. And OpenMP provides a simple and effective way to implement parallel solutions. This approach works best when the problem has independent computations, as in this case. And that's it. Thank you for watching. Bye bye.